My name is Ovidiu Bogdan. I'm foundry and material engineer, and I will present to you my results concerning the optimization of ingot geometry, casting technology, and chemical composition of a 20 tons 42 chrome molybdenum 4 ingot to minimize A-segregation and increase material homogeneity. First of all, I'd like to thank you for attending my presentation. At the beginning, I will tell you a few words about the experience I have in this domain, and then I will make actually the presentation. I worked for over 10 years with IMGB, a manufacturer of big ingots and forgings. Then I worked for several years as a researcher with Polytechnica University in Bucharest, and now I am the owner of Industrial Soft, a Montreal company specialized in development of software applications to improve the internal quality of forging ingots. In this presentation, first I will provide a short description of macro segregation type that has been taken in view, then the tools we have developed to mold design and the technique I use to assess A-segregation appearance. The integrated online ingot and mold design assistant and the solidification simulation software SimCAD has been used to analyze the A-segregation and put in evidence the influence of ingot shape, several casting variables, and chemical composition on the size and position of A-segregation area. This technique I will present refers to A-segregation, one of the types of macro segregation. We can find this kind of material heterogeneity in the zone of transition from columnar grains to large equiaxed grains. In this slide, we can see the A-segregation position on the longitudinal section of the ingot. Next, it's a sulfur print test taken in the A-segregation area. Sometimes the ultrasonic test does not detect the A-segregation channels. Instead, as observed in real products, because of material heterogeneity, we can have problems to meet the specifications concerning mechanical properties. Ingot and Mold Design Assistant is an online tool based on a mathematical model that allows to design ingots and molds using minimum data such as ingot weight, ingot H/D, ingot taper, and the number of sides. This tool can generate quickly ingot and mold projects having round, rectangular, or polygonal section and makes available instantly two-dimension drawings, three-dimension models, and prepare the geometrical data needed by SimCAD, the solidification and A-segregation analysis software. Here are several examples of mold and ingots projects that have been used to analyze the influence of H/D ratio and the hot top size on the distribution of A-segregation area size. The solidification simulation and A-segregation analysis software is also an online tool. It takes into account the material properties, internal sources, the heat exchange with the environment, thermoisolation, and exothermic materials. The software uses over 160,000 print elements to get an accurate geometric description of the model. The software allows online to choose a mold from a library of mold projects, the steel from a database, and set the pouring temperature of the steel. The needed time to compose the problem and display the results, as you can see in this slide, is about 20 minutes. The software has been validated in industrial conditions several years ago in cooperation with Cosipa, a steelmaking company in Brazil, and the results have been published into a technical magazine. See the list of references to get the paper and learn more about the conditions of the validation of the software. This flowchart presents the macro segregation analysis technique we have developed and implemented in the segregation analysis module of the software. As you can see in this flowchart, there are two branches. The left one calculates by simulation the cooling and solidification rate. The other branch calculates using the chemical composition of the steel, the critical value alpha, the value at which the A-segregation will appear. Then the software compares the value we got from both branches and plot the segregation area and regions that contain value below the critical value. Using laboratory experimental data, we have developed a mathematical model to evaluate the solidification conditions and establish the critical condition at which the A-segregation starts to appear. At the moment, our mathematical model is applicable to low alloy and carbon steels. More experiments must be done to cover other steels. If someone is interested in this kind of experiments, please let me know. In this report, to assess comparatively the influence of various variables on A-segregation, we have defined the segregation area ratio, the ratio between area affected by A-segregation and the longitudinal section area of the ingot body. Because in controlling the A-segregation, it's important not only the area of segregation, but also the size and distribution of segregates inside the segregation area. We defined the intensity of A-segregation as difference between the critical value alpha and local cooling conditions. To analyze the influence of ingot shape on A-segregation, the chemical composition of the steel that has been taken in consideration is in the first table. In the second table is the geometry data of the analyzed ingots. Here, the H-on-T ratio is defined as ratio between body weight and medium diameter. This slide shows the segregation distribution in ingot with HD ratio of 3, 4, and 5. These experiments show that the segregation area ratio strongly decreases from around 16% for an ingot with HD ratio 3.0 to around 2% for the ingot with HD ratio 5.0. The segregation intensity decreases as well from around 40% to below 6%. To analyze the influence of ingot taper on segregation, 3 simulations have been made with ingot having taper of 0.1, 2.0, and 4.0% and keeping the HD ratio and all other parameters unchanged. As you can see in this slide, the area affected by segregation is larger if the ingot taper is high. To analyze the influence of hot top size on A-segregation, these simulations have been made, keeping the same ingot body and HD ratio and changing the hot top size from 20% to around 13%. These experiments show that the segregation area increases from 6% for a small hot top to 11% for a bigger hot top size. In this slide is a summary of previous experiments. From the analyzed factor, the only variables that have a significant influence of A-segregation are HD ratio and the hot top size. To minimize A-segregation, we must choose an ingot with higher HD ratio and a small hot top size. To quantify how the pouring temperature has influence on A-segregation, a simulation series with pouring temperature between 1540 and 1600 Celsius has been made. The results show that there is a small increase of segregation area with increasing of pouring temperature. To analyze the influence of exothermic material on A-segregation, we made also three simulations. For one of them has not been added exothermic material. For the second one, the exothermic material has been 2 kilo per ton, and for the last one, 4 kilo per ton. The figure on the right side of the slide shows that the A-segregation area is practically unchanged. To analyze the influence of chemical composition on A-segregation, the elements that have been taken into account are in this table. The ingot size and shape are like in the other experiments, and the pooling temperature has been 1570 Celsius. To analyze the influence of carbon on A-segregation, three series of simulations have been made with the carbon content at the minimum, medium, and maximum limit allowed by the steel specification. The results of experiments show that there is a strong increase of the segregation area from 8% to 35% with the increase of the carbon content from minimum to maximum limit allowed. Even a small increase of carbon content gives a big increase of both the segregation area and segregation intensity. As in the previous experiments, the influence of silicon content on A-segregation has been analyzed for the minimum, medium, and maximum limit allowed by the specification. We see in this slide that the segregation area ratio increases strongly from practically 0 to 25%, with the silicon content increasing from the minimum to maximum limit allowed by specification. To minimize A-segregation, a low silicon content is recommended, but this may have a practical interest only if the steel is poured using a vacuum carbon dioxidation technology. In the following experiments, the molybdenum content taken into account is between 0.15 and 0.30%. This slide shows that the segregation area decreases from 20% to 4% with the increase of the molybdenum content from minimum to maximum value allowed. Because the decrease of segregation area is so significant with the variation of molybdenum in the limits of steel specification, we can conclude that for this steel, the molybdenum content may be an element by which we can control the A-segregation. This slide shows a summary of the influence of chemical element on A-segregation. Here we can see again how important is the influence of carbon and silicon content on the size of A-segregation area. Also, we see in this slide that the manganese and chrome content has low or does not have influence on A-segregation area size. The experiments we made so far have been for an ingot for a forged bar, but if we need a plate to get an ingot with A-segregation, we have to choose an ingot with another shape. In this clip, we are going to see the mold, ingot, and A-segregation distribution for a polygonal ingot with HD ratio 2.0, and also the molds, ingots, and the segregation distribution in rectangular ingot with size ratio between 1.0 and 2.5. All the ingots have the same weight, 20 tons. At the end of the clip, we are going to see that in the rectangular ingot with the size ratio 2.5, the segregation has practically disappeared. For the polygonal ingot, the A-segregation area is around 35%, and for the ingots with rectangular section, the segregation area ratio decreases from 27% for the rectangular ingot with the size ratio 1.0 to 1% for the ingot with size ratio 2.5. Having in view the results of the experiments and the solidification analysis, we can conclude the following. To minimize A-segregation in a forged bar, we need a cylindrical ingot with high H-on-G ratio, small hot top size, low carbon and silicon content, and high molybdenum content. To minimize A-segregation in a forged plate, we need a rectangular ingot with a high size ratio. Cooling temperature, ingot taper, and manganese content have low influence of A-segregation. Exothermic material and chrome content does not have influence on A-segregation. Mold design and A-segregation analysis are easy-to-use tools available online with a PC, Mac, tablet, or a smartphone to design molds, analyze segregation, and choose the mold function by steel grade and forged shape. At the moment, in the Mold Design Assistant library, there are almost 200 mold projects, and the segregation analysis model has over 300 steel grades in the database. If someone is interested to add their molds to this library, please contact me to give you more information. I finished my presentation, and I'd like to thank you very much for listening to, and if you like to ask questions, I'll be happy to answer them. Also, if you like to give a try to the software I presented, please check the address you see on the screen. Thank you again.